14.3 covers the things that are going to affect how things form solutions, so how things dissolve. And we're going to look specifically at how temperature, pressure, and polarity affect the formations of these solutions. So first, we need to know some terminology. The first word that we need to know is solvation. So this is the process of surrounding solute particles with solvent particles to form a solution. We know that solutions are made up of solutes and solvents. So when the solvent is surrounding and kind of dismantling how you saw in the simulations, dismantling the solute and separating it and hydrating it, we call that solvation. The solvation in water is called hydration. So hydration is just a specific type of solvation where the solvent happens to be hydrated or water. Just like when we talked about aqueous solutions or solutions that are in water, hydration is the process of solvation. In chemistry, the solvent that we use most often is water, so therefore we have to surrounding that concept. Water, being a polar molecule, is a good molecule to help dissolve a lot of things like ionic salts. So when the attraction between the dipoles of the water molecules and the ions are greater than the ionic attractions between the specific ions, that's what allows the salt to be dissolved. So you have attractions between ions, that's the ionic attractions, and then you have the attraction between the polar water molecules and the ions. Because the attraction between the polar water molecules exceeds that of the attraction between the ions, that allows the ions to be hydrated. You can see in this figure below, they are dumping some salt into water, and then here's a model to represent what is happening. So here we see the undissolved salt crystal, the positive and the negative attractions, and then we see a few ions being taken off of that crystal and being hydrated. As you saw in the simulation, the negative ions are surrounded by the water molecules, where the positive side of the water molecules is facing the negative ions, so negative and positive attract. And then the positive ions in the salt, in this case the sodium ions, they are attracting the negative side of the water molecules. Positive and negative attract. So depending on the charge on the ion, chloride, negative, sodium, positive, that will dictate the orientation of the water molecules. This is obviously showing you just a slice of what would be happening, but this is also happening in a three-dimensional space. So you would have so many water molecules clustered around these ions, you wouldn't even see the ions present because they'd be surrounded by all water molecules. So this is the same thing I just showed you. Here we have the positives, the chloride, the green one is negative, and then you have the positive sides of the water molecules facing the negative chloride ion, and then you have the opposite. So you have the positive sodium ions and the negative side of the water molecules facing that. So positives and negatives attract. And here you have the undissolved, in the process of dissolving, salt crystal being kind of dismantled by those water molecules that are coming in and solvating and carrying away those ions and spreading out. Diffusion is playing a role here. As we go from a higher concentration to a lower concentration, those hydrated ions are going to drift apart and they will spread out from high concentration near the salt crystal to low concentration in other parts of the solution. That obviously takes a while though. We saw in the simulation how other molecules such as sucrose, which is table sugar, are going to have different interactions with that water. Here, this is a cool picture of a sugar cube in water, and you can kind of see that you have really high concentration sugar in solution, and it's coming off near the sugar cube. You see the diffraction of the light because of the higher density solution here. As time progresses, all of this sugar will dissolve and the higher concentration solute will spread out through diffusion going from high concentration to low concentration. This is what a sugar molecule looks like, or the model of a sugar molecule looks like. You'll be reminded that we could simplify this model a lot, where every time we have a carbon, we could represent it just with a bend or an end. And therefore, we could remove all the carbons and then assume the hydrogens in this model and just show all of the oxygens. But one thing that should really stand out to you is the OH groups. So here, 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 here. We previously learned that OH groups allow for hydrogen bonding to occur, one of our intermolecular forces. So all of the water molecules highlighted in green in this model show we could see how the water molecules are interacting with this large sucrose molecule. So very similar to how the water molecules hydrated the individual ions of the salt, the water molecules are hydrating the entire molecule of sucrose. We're not able to separate off individual components of the sugar. Instead, the entire molecule is the unit that's being hydrated. So that's a big difference between salts and things like sugar. And it's going to be based on the bond type. So ionic substances are salts, and then covalent substances are things like sugar. So sugar to be a covalent substance, it's going to dissolve differently than your ionic salt. Other types of things like oil do not form a solution at all with water because there's little attraction between the polar water molecules and the nonpolar oil molecules. So you have to have some sort of attraction between the water molecules and what they're dissolving. Otherwise, we would call it hydrophobic, and it's not going to want to interact with the water at all. So the salt had the positives and the negatives, allowing it to interact with the polar water molecules. The sucrose has the OH groups, allowing it to interact with the water molecules. But something like oil, which would just be a long chain of carbons and hydrogens, having no polar regions in it at all, is not going to be able to interact with the water. So I think you know that if you were to pour some oil in water, it's going to sit on top, and it will have very little interaction with the water. During solvation, the solute must separate into particles and move apart, which requires energy. So when this occurs, we have an energy change, and we call that the heat of solution. Some things, when you solvate them, so when you dissolve them, they will get very hot because we have a net change for the heat of solution, a net change of the energy that's going to be exothermic for the process of dissolving. Other things, when they dissolve, while less common, will get cold as they dissolve. So you might recall when we were going over signs of a chemical change, and this is actually a counterexample because it was not a chemical change at all, but I took some ammonium nitrate, a special salt, that when you dissolve it, it gets colder. And then I took the flask around the room and I said, hey, feel this, it's very cold. And you said, oh yeah, it is cold. That happens because of the change in the heat of the solution. There's other things where if I were to take, for instance, a concentrated sulfuric acid and I were to add it to a little bit of water, it's going to get so hot that it will be boiling because of the heat of the solution is so great. There are three main things that are going to affect the rate at which something is going to dissolve. So here I have a sugar cube. It's being dissolved in an iced tea. And then here's a hot tea. So we have tea, tea, and tea, and we're dissolving sugar in each. The ability / the rate in which that sugar is going to dissolve in these various teas, one that's just an iced tea with the sugar cube sitting at the bottom, one that's being stirred, and one that's hot, is going to be different. Because there are different things that can affect how or the rate in which something is going to dissolve. The first bullet point here is stirring, shaking, or you could call it agitation, will aid in the solvation of a solution. If you think about it, I told you and showed you in the simulation that the water molecules need to come in and take those molecules of sucrose away, or the ions of the salt away. Solvate each individual particle, whether it's an ion or molecule, and then it will diffuse at a low concentration. Well, what can speed that process up? Well, if they're aided that can speed the process up. So it allows for the water molecules to get in and take their molecule or ion away more quickly. So stirring or shaking helps dissolve things quicker. So you can see in those first two images, the one where I just have some tea and I put some sugar in there, that sugar cube is going to take a while to dissolve. However, if I were to stir it, just like in the second image, I could speed that process up. I could also break the solute into smaller pieces. This increases the surface area and allows more collisions to occur, thereby increasing the rate of solvation. Let's go back to one of the particulate diagrams here. This one. So this is a small crystal of salt. However, it gets across that there are ions that are not exposed to the water yet. They are hidden further within the crystal. So if you have a large crystal, there's more ions that are you can kind of hidden and not exposed to the water. Those ions that are not exposed to the water cannot be solvated yet. You have to wait until the outer layers are first removed, and then they can be solvated. So if we were to take this salt crystal or sugar cube and we were to crush it up, maybe with a mortar pestle first, or just a spoon in the case of the tea, if I were to crush that up, that spreads out the amount of exposed solute, and therefore it can solvate. Increasing the surface area by crushing, more surface area exposed to water, the more quickly it's going to dissolve. And then the last thing, it's very similar and has similar reasoning to the first two, and that's as temperature increases, the rate of solvation increases as well. So if I have a hot tea, the last picture, versus a cold tea in the top picture, and I put a sugar cube in each of them, we would see that the hot tea, the sugar cube would dissolve much more rapidly than the cold tea. And this has to do with the movement of the water molecules. If you have a higher temperature, as the temperature suggests, we have more energy. Remember, temperature is a measurement of kinetic energy. More kinetic energy, the water molecules are moving more rapidly. They can get in, take a sugar molecule, take it away, spread out somewhere else into the solute or into the solution, and then you just have a more rapid turnover and solvation followed by diffusion of those different molecules within the solution. So higher temperature, more movement of particles. So anytime you're increasing the ability for the solvent to come in and surround the solute and then diffuse, that's going to lead to a higher rate of solution. Whether it be agitation, shaking, stirring, the first bullet point, or crushing it up, increasing the surface area in the second bullet point, or just having faster solvent molecules, having a higher temperature. All three of those things can aid in speeding up the rate of solvation. Different salts, different substances can have different solubilities. The solubility depends on the nature of the solute and the solvent. So we need to have some sort of interaction between the solvent and the solute. Otherwise, we're not going to form a solution. There are some things, like I already gave you the previous example, where oil and water, the oil is not going to dissolve in the water to any appreciable extent. And that's because there is not much interaction between a polar water molecule and a non-polar oil molecule. So whenever you pair up a solvent and a solute, the more interaction you have between the solute and the solvent, the more soluble it's going to be. The less interaction, and remember when I say interaction, we're talking about intramolecular forces, van der Waals attractive forces, dipole-dipole interactions, and hydrogen bonding. So whenever you have more of those interactions due to the polarity of the solvent or the solute or both, that's going to be more or less solubility. So here in this model, we have the solubility versus the temperature. So solubility on the y-axis and the temperature on the x-axis. We see the solubility is being measured in grams of solute per 100 grams of water, which is a conventional measure of solubility. So in other words, if I have 100 grams of water, how many grams of solute can be dissolved in that water? Some substances it's a lot, Some substances, not very much. Some substances, you can actually surpass the mass of the water. So if I can actually take sugar, I can dissolve more than 100 grams of sugar in 100 grams of water. And that's how you make syrup. Have such a high viscosity. We can then describe these solutions as being saturated or unsaturated. So if you are at max solubility, no more will dissolve, then we would describe it as being a saturated solution. If you still have more mass of solute that can be dissolved, then we have an unsaturated solution. So looking at this graph, we can see that depending on what the temperature is and the identity of the substance that's being dissolved, in this case these are all salts, their solubility will vary. Look at the green line, sodium chloride, conventional table salt. You can see as we change the temperature from 0 degrees Celsius to 100 degrees Celsius, the temperature of the solvent, our solubility goes from roughly 35 to slightly over 40 grams of salt, capable of dissolving in 100 grams of water. So by raising the temperature, we don't have any large increase in its solubility. But if you look at something like the magenta line, potassium chloride, that's going to be chlorate, potassium chloride, KClO3. You can see that at 0 degrees Celsius, the solubility is roughly 5 grams, so not very much capable of dissolving in that cold water, and it is going to go up and surpass the solubility of sodium chloride at 100 degrees Celsius as it gets to roughly 50 grams. So we see a very large change in the solubility based on the temperature for potassium chloride. Some of them are very steep. We change calcium chloride, for example, starts with a very high solubility at 0 degrees Celsius. There's like 60 grams that can dissolve in it. And once we get up, it's hard to read it from over here. Once we get up to roughly 30 degrees Celsius, we are surpassing the 100 gram mark. So we can get more mass of that salt in the water. Some of them decrease. Here we have cerium sulfate, a very uncommon salt. The solubility decreases as temperature increases. So saturated solutions, as I earlier mentioned, is something where the maximum amount of dissolved solute is present in the solution. No more will dissolve. So this is temperature dependent. So let's say I have water and it's at roughly 25 degrees Celsius, and I dissolve some salt. I stir it, it dissolves. I add some more. I stir it, it dissolves. I add some more. Stir it, it dissolves. I add some more. This time I stir it, nothing happens. It just settles to the bottom. No more salt will dissolve. All of the spaces that are available in that water as a solvent to dissolve and solvate the salt, the ions of the salt, they are all occupied. There's no more ability for that salt to dissolve. So it just settles to the bottom in the crystalline form. That is what we call a saturated solution. So we can affect the solubility by changing the temperature, as you saw in that last graph, but every temperature is going to have a maximum solubility associated with it. A good way to think about it is thermal expansion. We know that when we heat a substance up, specifically in this case water, when we heat up the solvent of water, the space between the particles increases. We have expansion. So think about it as those spaces are the spaces that are occupied by the solute. A warmer solution has more space for more solute. So typically what we see is when the solvent of water increases in temperature, the amount of solute that can be dissolved and occupy those expanded spaces is going to increase. So solubility increases with temperature and it decreases with cooler temperatures. So this diagram here, well, it's a picture and a model. On the right, we could see we have some type of salt, probably a copper to something, probably copper to sulfate salt, and the solution is saturated. And if you look closely, you can see that it has some salt at the bottom, suggesting that as much of what was going to dissolve has dissolved. And at this point, we see the model. The amount of ions in solution is at equilibrium. So some ions are leaving the crystalline form and going into solution at the same rate that we have other ions that are forming crystals. So we don't really see any net change in the rate of solvation here. There exists a state in which some solutions can achieve. This is called a supersaturated state. This is a state where you can raise the temperature and dissolve more salt. And then what you do is you slowly cool that solution. A lot of solutions will start to crystallize the dissolved salts as it cools. Some solutions, like this one, you will not have any crystallization. So as you cool the solution from 50 to 40 to 30 to 20, as you get back to something close to room temperature, none of the salt will crystallize. You would think it would, because when you were back at 20 degrees Celsius originally, you couldn't dissolve any more salt in it. You had to raise the temperature. So I'm at 20 degrees Celsius. I add some salt. I stir it, it dissolves. I add some salt. I stir it, it dissolves. I add some salt. I stir it, it doesn't dissolve this time. So what do? I raise the temperature from 20 to 30. That salt that wouldn't dissolve at 20 has now dissolved. I add a little bit more, it dissolves. I add a little bit more, it dissolves. Add a little bit more, it doesn't dissolve. I raise the temperature from 30 to 40, 40 to 50. And I could repeat this process until I get to the point where I have a hot solution and I've dissolved a lot more salt than I was able to at 20 degrees Celsius. Now that I've dissolved that salt, I will then drop off the temperature back to the original temperature of 20. And lo and behold, all that salt is now staying in solution. This solution is unstable. It is what we call supersaturated. Because it is unstable, a brief or a shock to the system, which can be by using something like a seed crystal. So if I were to drop some undissolved salt in the solution at this point, what will happen is a rapid crystallization of this solution. And so that's what you see here. You have the supersaturated solution in the left panel there. In the middle panel, they drop that seed crystal in, and we see an immediate crystallization around that seed crystal, and we're making these beautiful fibrous crystals of sodium acetate on the right. Exothermic process. Let's find a quick video of this on YouTube. I haven't vetted these videos. I'm just going to type in a quick Google search, sodium acetate solution. It's going to auto-complete the crystallization for me, because again, this is a very common salt to do this with. And looks like this is a good video I found. Here we are. Has more sodium in it that ought to be in it based on the solubility of that salt. So we can exceed the natural solubility at a certain temperature by using the method that I previously described. Here is an example of supersaturated solutions. So hot spring mineral deposits. So this is one which I would presume would be in Yellowstone because it looks like a hot spring from Yellowstone. If you look carefully at this diagram, you see some salt on the edge. So this yellow and looks green under the water. This is a bacterial culture. But the white on the edge, that is salt. And so what happens is you have this hot spring. It's a fairly hot temperature, and you have all these salts dissolved in there. Well, as this water has a very high level of salinity approaches the edge and it starts to dry up, we have a rapid crystallization of whatever salts you have, and that's going to form this salt on the edge. So this is a very high salinity water in a hot spring. This is just a list of solubilities of different substances in water at various temperatures. Like I previously mentioned, grams per 100 grams of water is a common way to describe solubility. So we would be able to graph all of these things. So I'd be able to graph the solubility versus the 0 degrees Celsius, the 36.4 degree or the 36.4 solubility against the 20 degrees Celsius, and I would be able to make a curved line for each of these substances showing the solubility. At the bottom of this table, you can see that I have three substances, ammonia, carbon dioxide, and oxygen, and you'll note that they have ammonia not being a good example, but carbon dioxide and oxygen have very low solubilities. Gases having higher kinetic energy don't want to stay in solution, so therefore it's hard to get very much of them in solution. But we do. That's how we make soda. So if you're going to make soda, we carbonate the drink. The reason why we call it carbonation is because of the carbon dioxide that we're using to dissolve in the water. So we can have carbon dioxide dissolved. It is soluble in water. We can dissolve more of it with a higher pressure or with a cooler temperature. So gases actually want a cooler temperature for the solvent. And the reason why that is because the cooler temperature slows down the gaseous water molecules. It decreases their kinetic energy and it increases their propensity to stay in the solution. So oxygen, carbon dioxide, we could see that they are more soluble. So see, we have 0, 20, 60. They're more soluble at the lower temperatures. So you can see that carbon dioxide solubility drops from 1.7 to 0.9 when we go from 0 to 20 degrees Celsius. And it goes from 0.9 to 0.4, from 20 to 60 degrees Celsius. So we see the solubility dropping for gases as we increase the temperature, but we see the opposite trend for salts and things like sucrose. Ammonia, you can see how it's extremely soluble at cold temperatures. We can get a ton of ammonia dissolved in water at 0 degrees Celsius, but it, again, like the other gases, is going to increase with the increased kinetic energy, the increased temperature. Of course, dissolved oxygen being very important for aquatic ecosystems. Here we have a soda. We have CO2 dissolved in the soda. That's what creates the bubbly texture of the soda. And they will pressurize the soda, forcing more carbon dioxide into the solution than would actually be soluble at a normal pressure. But as soon as you release the pressure, so when I twist the cap on the soda bottle, you hear that, which lets you know that the now pressurized system above the soda is at atmospheric pressure. And what do you see with the solution, the soda? A lot of the carbon dioxide immediately bubbles out. And that's because you suddenly decrease the solubility of the carbon dioxide in that solution, because solubility also varies with the pressure. So gas solubility is governed by Henry's law. So you could see that this is a direct proportion. So solubility S is directly proportional to the pressure. So as we increase the pressure of a system, we're going to increase the solubility of a gas. So this only happens with gases. It does not happen with solids. How do they get this equation here? Well, to go from a proportion to an equality, you introduce an equal sign and a constant. Solve for that constant. We have S over P equal to the constant. Sorry, I'm writing with a mouse here. And because this is a constant, K is a constant, and S and P are variables, we could have S1 P1 equal to K, or we could also have S2 over P2 equal to K, or we could have S3 over P3 equal to K. We could change the solubility and pressure to whatever they will be, and will always be equal to this same constant value. So we could then say that S1 over P1 is equal to S2 over P2 equal to S3 over P3, and that's how we're getting this equation, which is Henry's law. So what Henry's law allows us to do is it allows us to have a certain gas dissolved in a certain pressure system, and then we change the pressure on that system, and we see how the solubility changes as a result. So here is an example for Henry's law. If 0.85 grams of a gas at 4 atmospheres of pressure dissolves in 1 liter of water at 25 degrees Celsius, how much will dissolve in 1 liter of water at 1.0 atmospheres of pressure, the same temperature? So there are some red herring values in this problem. We are dealing with Henry's law, so we really just want to deal with the solubility and the pressure. So what is the solubility? Solubility is 0.85 grams for every 1 liter, and that shows us in the problem. 0.85 grams of a gas dissolves in 1 liter of water. So 0.85 grams / L, grams per liter. The pressure is starting at 4 atmospheres, so that's P1, and we're changing the pressure from 4 to 1, so 1.0 is P2, and we want to know what S2 is, so that is our unknown. So we use Henry's law. We plug into Henry's law. Well, actually, we're going to rearrange Henry's law first to solve for S2. Then they'll plug into it. You could plug in first and then solve. That's what I would do. And we end up finding that the solubility of this gas is now going to be 0.21 grams per liter. So as expected, as we decrease the pressure from 4 to 1, so we go from a pressurized system to a system that's more like atmospheric pressure, the amount of the gas is going to decrease. So we previously had 0.85 grams for every 1 liter. Now we can only have 0.21 grams for every 1 liter. That's it.